Can you double the energy of a photon without changing the speed of light? It sounds impossible. But with just one simple change, the answer is yes. Let's find out how. A photon inside a perfectly reflecting cavity has an initial wavelength of 600 nanometers. After adiabatic compression, its wavelength decreases to 300 nanometers. You have to determine that by what factor does the frequency of the photon change, and by what factor does the energy of the photon change. Before solving the numerical, let's understand the physics. The speed of light never changes. It is constant. So if the wavelength becomes shorter, what must happen to the frequency? Remember that the speed of light is expressed as the product of frequency and wavelength. And as speed of light is constant, it means that frequency and wavelength are inversely proportional. A smaller wavelength always means a higher frequency. And because the energy of a photon is expressed as Planck's constant times the frequency, or we can say that the energy of the photon is directly proportional to the frequency. It means that higher the frequency, higher is the photon energy. Notice something remarkable. Nothing about the photon speed changes, only its wavelength does. Yet its energy changes dramatically. Now let's solve the numerical. We are given that initial wavelength of the photon is 600 nanometers and the final wavelength is 300 nanometers. Using the relation c, the speed of light equals to its frequency multiplied by wavelength, so frequency can be expressed as c over lambda. C is the speed of light. Now you can write this relation for the initial frequency and the final frequency of the photon. The initial frequency will be expressed as c over lambda 1 and the final frequency f2 is equal to c by lambda 2. Now dividing equation 2 by equation 1, you will get f2 over f1 equals to c by lambda 2 over c by lambda 1, which is equal to lambda 1 over lambda 2. Rearranging this equation, c will be cancelled and you are left with lambda 1 over lambda 2. Now putting the values, you will get the ratio of f2 to f1 equals to 2. It means that f2 to f1 equals to 2, that is f2 is equal to 2 times f1. The frequency, final frequency is 2 times the initial frequency. It is doubled. Now the energy of photon is expressed as h times f, where h is the Planck's constant and it is constant. So the initial energy of the photon is equal to hf1 and the final energy is h times f2. Now taking the ratio of these two energies, we'll get E2 by E1 equals to HF2 over HF1, which is equal to F2 over F1, because again the Planck's constant in both the relations will be cancelled. So E2 by E1 is equal to 2. Using the value of the ratio of the two frequencies, F2 to F1 is equal to 2, which we have already determined. So E2 is equal to 2 times E1. This means that the final energy of the photon is doubled. Now here is the beautiful part. Nothing was added to the photon itself. No new particle appeared, no extra charge, no change in the speed of light. The only thing that changed was the wavelength. A shorter wavelength means the electromagnetic field oscillates more rapidly. Higher oscillation frequency means higher photon energy. Sometimes changing the rhythm of nature changes the energy of reality. Now here is something to ponder. If compressing space makes wavelengths shorter, and shorter wavelengths means more energetic photons, are we really increasing the energy of the photons? Or are we changing the allowed electromagnetic modes inside the cavity? Physics often begins with numbers, but its deepest lessons lie in the questions those numbers inspire. If you enjoyed this challenge, leave your answer in the comment. Subscribe for more physics reflections. And remember, stay curious, stay conscious.